Okay, so we're starting chapter 4, which is nice because we are now bringing to conclusion the first part of the course on air pollution and air quality. So it's nice to kind of look forward to saying, okay, we've now concluded this first part. Okay, so here's the slides. You just download these. I think I'm just going to come out in front. So some of this is already on D2O, you've already read it. The images that I put there are from Mount St. Helens, and I'm not sure how old you all are, but I had the privilege of visiting the Mount St. Helens site. It was a pretty fascinating area. So you can watch the video, you can go to YouTube and find all kinds of videos because a lot of the consequences of the volcano erupting were captured on film. And there's a lot of really interesting footage you can see. It was a very consequential event that sent ash flying into the air and covered an enormous part of the United States with ash and brought a lot of acid back down to the earth. So that's one of the things we're going to talk about is why did that happen? To understand why a volcano leads to acid rain and then acid deposition on the ground requires a little bit of science to understand that. Not just acid-base chemistry, but redox chemistry as well. Just doing the usual, make sure I hit the record button. I seem to do that every time I do this. Okay, so not too much housekeeping that you haven't seen on D2L, the preview of coming attractions. This is primarily a qualitative chapter, like a lot of the chapters, and in this case, I'm going to probably do more chemistry and math than the book actually does. The book actually just sort of leaves some ideas hanging out there, and then there's an appendix in the book that goes to this. Redox chemistry, balancing a redox equation is one of the things that the book doesn't do a ton of, but your OpenStax accompanied general chemistry book does that, and I think there's some appendices, but I'm going to do a little bit more than what's in the book, because I want to focus on math and chemistry in these lectures and not write a bunch of qualitative stuff on the board, or at least minimize that. So everything else about the chapter is on D2L, so I don't need to go into a lot of preview coming attraction questions. Okay, so get your notes set up. This is Roman numeral chapter 4, and it says selected consequences of outdoor and indoor air pollution, and it is selective. And one of the assignments you'll get to select 2 of 4, so a menu of topics. 2 of the topics are indoor, 2 of the topics are outdoor, so you can choose one or mix and match one or the other as you see fit. Again, that's on D2L. Okay, so the thing we're going to focus on first, and I'm not going to copy down this definition, is they focus on acid rain. You see the sections in the book that are on there, and precipitation comes in a couple of different forms, rain, snow, fog, that's fine, and the idea is acid rain has a low pH than unpolluted precipitation. Well, that's kind of obvious, that's why it's called acid precipitation, acid deposition, acid rain, if it is indeed rain. Okay, the second slide, so if you want to, you can copy down the definition, that's fine, no problem. The second slide, I found this graphic, it's okay. It's basically making this point, and if you look there, that's not a typo, that's not equilibrium problem or problem 4-15. We're going back to something from the previous chapter that I just think makes more sense for this chapter. I'm not sure why it was in the previous chapter, but it doesn't matter, we're just going to cover it anyway. Is how do we go through some of the chemistry and the math to illustrate this idea of acidic precipitation. And the graph that's there, it's somewhat useful. It illustrates this concept. And I'm going to write that. I'll start with this on the board. As you put more carbon dioxide into the atmosphere, more of it dissolves in water. So as the pressure of CO2, or I should say the partial pressure of CO2, because remember it's not just pure CO2, it's partial pressure in the mixture, convoluted or complicated mixture of gases. As you increase that amount, well, it dissolves more in water. There's just more of it. There's more pressure. The more goes into water, either in a river, a creek, a lake, which is aquatic chemistry, or deposition or precipitation in the atmosphere. That's called Henry's law. And this graph shows that in a rather drastic fashion. The reason I picked this is because you see how the graph is shaped. And it goes up like this and over. And these are under enormously stressful conditions. So under very low pressures, in fact, and the x-axis is atmospheres, right? Under low pressures, the relationship is easy. As the temperature gets colder, more dissolves, but as the pressure increases, and this graph takes pressure to an extreme, which we would never, ever, ever see in an environmental situation. What does this go up to, like 500 atmospheres? No, you're never going to experience that kind of pressure in anything except a very controlled laboratory environment. But the graph makes the point, okay? And here's the point. So we're going to talk about carbon dioxide and naturally acidic precipitation and some of the math that's involved with that. Okay, so you'll need a calculator. I don't think you need a periodic table for this one. And we're going to try to do this in one video. So waters are naturally acidic because you have carbon dioxide from natural processes. We get into trouble when we start to put an inordinate amount of carbon dioxide into the atmosphere. Burning of fossil fuels is the most common example. That puts a lot of CO2 into the atmosphere. I'll make some comments about that as we go along. So when we start talking about the chemistry is the same, whether or not the CO2 comes from a natural process, just the normal carbon cycle, if you're familiar with that term, or an unnatural source like the burning of fossil fuels. It doesn't matter. The chemistry is largely the same. And this is what we're looking at, is carbon dioxide as a gas, it's fine, it comes into contact with water. In this case, we're talking about water that is in the atmosphere, the stratosphere or troposphere, doesn't really matter in this case, and then it comes down to the earth. But we'll talk about this again in the unit on water chemistry, which will be the same chemistry. And we produce something we just call carbonic acid. And there's always some debate about what exactly carbonic acid is. Now, I'm just going to read this here. This is called Henry's law. And you can look this up. I'm not going to copy this definition down. I have it in my notes, but I'm not going to rewrite it. Henry's law says this: the amount of an ideal gas, that's important, because ideal gas means relatively low pressure, relatively low temperatures. The graph that goes up and over that I have on your slide, way, way towards the origin is what we're talking about. It gets non-ideal at high pressure, so those are irrelevant for environmental chemistry. So the amount of an ideal gas that dissolves in a given solvent, water in our case, at a given temperature, because that matters, is directly proportional to the partial pressure of the gas. Here we're talking about CO2. So how do you just paraphrase that? The higher pressure of the gas, the more it dissolves in water for an ideal gas. The way we can do that symbolically is that the partial pressure of whatever gas we're talking about, so partial pressure, is going to be proportional to how much dissolves in a solvent. So for this specific example, this is not all of Henry's law here. This is an example of Henry's law. The partial pressure is proportional, that's what that means. It's not equal, it's proportional, if you haven't seen that symbol in a while, to the concentration of H2CO3 that's formed. That may just sound kind of obvious. Like, well, if you have more CO2 in the air, it's going to produce more carbonic acid in an aqueous system, regardless of where that aqueous system is. And that's how we express this symbolically. And then we can actually turn this into an equation. Like we do all the time in science. How do you take a proportionality and make it an equation? Well, in this case, you can do it a couple of different ways, but I want to make sure I do this one here the correct way. Is the concentration, because ultimately what we're after, folks, why am I doing the math? Ultimately we're after, this is an acid. More specifically, this is a weak diprotic acid. If you haven't had a chance to review the acid-base chemistry from OpenStax, go back and look at what those words mean. Okay? It's weak and it's diprotic. So the amount of carbonic acid that is formed in water, I'm going to not put the AQ all the time, is equal to some constant times the pressure. We take a proportionality and make it an equality by using a constant. I know some engineers often refer to those constants as kind of fudge factors or things like this, but it's not really a fudge factor. And that is called the Henry's law constant. Now, the thing is, the Henry's law constant is not constant for all conditions. It's a constant for a given solvent, water in this case, and at a given temperature. So it's not the same number like the speed of light. The speed of light is constant under all conditions. This depends on temperature and well, what the solvent is. In this case, our solvent is pretty much always water. And then just to give you an example, I think this is the only one the book uses. The book always tends to use 25 degrees Celsius. That's reasonable. We can look up other ones. I think maybe somewhere down the line I have you look up some other ones. It is 3.4 times 10 to the minus 2, and the units are molarity per atmosphere. And I'll let you think about that for a second. The units make sense. If you solve this equation for kH, this is molarity. If we use atmospheres as our unit of pressure, then yeah, that's what the units would have here. Now this is for CO2 in water at 25 degrees Celsius. So please don't assume that's just a number that applies to everything, all the time, every molecule, every solvent. It's not the case. This is like an equilibrium constant when we get to acids and bases. Okay, that's fine. And I'm going to come back to this concept here. I think I can fit this in before I have to erase it and start doing math. Yeah, great. Don't think I need my phone. H2CO3 is a weak diprotic acid. And that's called carbonic acid if you really want to name it up here. So what does that mean? How do we take that concept? And what that means is that if you take H2CO3 and it goes into water, it will set up an equilibrium. That's what weak acids do. Strong acids are not an equilibrium. Strong acids completely dissociate into its component parts. That's the difference between strong and weak. Weak means partially dissociated, strong means completely dissociated. So this is a true equilibrium where only a small amount of H plus will dissociate, leaving behind HCO3 minus. Now, I might as well just get the vocabulary here. So this is carbonic acid. We often refer to these as protons or hydronium. And this is called bicarbonate. This is a bicarbonate anion. We're going to talk a lot more about this chemistry when we get specifically to the section on aquatic chemistry. And all of this is aqueous. And you might recall that we have what's called an equilibrium constant. And this is an equilibrium constant for acids. This is called an acid dissociation constant. And like all equilibrium constants, it's the concentration of the products multiplied together. And if there were coefficients here, like 2, 1, whatever, you would put a power. But these are all coefficients of 1. So it's H plus to the first, carbonate to the first. And this ratio of the dissociated species to the neutral, original, in this case, weak diprotic acid, that ratio tells you how far does it go to the right, how much dissociates. And because it's a weak acid, in this case, it's, I think this is the same one in your book, 4.5 times 10 to the minus 7th. And if you think about units, I'm actually not going to get hung up on units with this, because I want to remember chemistry is a tool for us. This is not a Gen Chem class. But if this bothers you, this is going to be molarity times molarity divided by molarity. So this is going to have the units of molarity, but for our purposes, we don't need to worry about that. And again, this is temperature dependent. And you can simply look up a table of acid dissociation constants for carbonic acid, and just to let you know, you're going to find 2 acid dissociation constants. One for HCO3, then, H2CO3. HCO3 can go on and do another round of dissociation, which will be important in the next unit on water chemistry. Okay, so those are the basics. What I'd like to do now is to actually apply these concepts and do a math problem. And the math problem we're doing is, I'm sorry. Look at my notes when it's on the slide. So that's the background information. So equilibrium math, problem 3-15. So go back to chapter 3. And what we're trying to do here, I'm only going to do part A, I'll let you do part B. So what we're trying to do is what is the pH of an aqueous system when the partial pressure of carbon dioxide is about 390. Now you might recall that 390 parts per million was an approximation of the CO2 content at the time of the writing of the book. So 2012, I think. That number has been creeping up. Remember the hockey stick graph that goes up. So that number is getting higher. So a takeaway from this, before we start doing all this math, as the CO2 goes up, the pH goes down because that means it's more acidic. So this is where when we talk about acidification of an ocean, acidification of a freshwater system. What does that mean? Well, that means that the CO2 is going up, the H2CO3 concentration is going up, and the pH is going down. But I don't want to just talk about those relationships. I want to show the math behind those relationships. So we'll do this one together. Let's assume we have 390 ppm. And you might recall, I think we're above 400 parts per million right now. In fact, for extra credit, if you want to, go look up the current average CO2 partial pressure globally and repeat the calculation we are about to do. Oh, part B, I put there 560 parts per million. If we get to that level, we're in trouble for a lot of reasons if we get to that level. So you can tell by my probably dark humor there. Okay, let's do this. I'm just going to need a second to erase. I'll just keep talking a little bit. We're going to apply this equation and do some math. And this is going to take you back to some Gen Chem. Okay, the one thing we're going to need is a way, and this, when I first taught this course, this confused me, but I don't know why, because it seems obvious now, is how do you take a parts per million measurement? So 390 parts per million. And how do you convert that into atmospheres? Sure, remember all those unit conversions we did in the last chapter? Some of those were pretty tough. And we can do that, but it's actually pretty simple. If you know the concentration in parts per million, the partial pressure is simply a derivation of that. I don't know why, this took me a long time to get a hold of this. I don't think I talked about this in the previous lecture, so if I did, I apologize. So 390 parts per million. What does that mean? That means we have 390 molecules of CO2 per That's what that means. Molecules per million of other molecules. That's fine, that doesn't really answer the question, does it? For an ideal gas, remember what an ideal gas is. An ideal gas is something that's bouncing around off of each other or off of the container or just out in the atmosphere. So what we can actually do is use any unit here. We don't have to use molecules. So you could use this. This seems very strange, but I think this is the way to think about it. That if we used atmospheres, this would be 300 atmospheres of CO2, which is ridiculous. That's 390 atmospheres. I mean, right now, everything we're in is about 1 atmosphere. In 10 to the 6th atmospheres total. And that seems very strange, but this lets us do something really simple. We need a number for the partial pressure of carbon dioxide that is measured in atmospheres if we're going to use the Henry's law constant. But this is easy. Isn't that easy? 390 divided by a million. 1, 2, 3, 4, 5, 6. There you go. So that's a simple way to go from ppm to atm. And I don't know why that took me a while to get my head around. If it makes sense to you, then go with it. Okay, so we have that. So we have a number to go there. So now we can start doing math. And my notes here are not that explicit, but you follow the same procedure. So, step 1. Well, this is not going to come as a shock. You take the data you're given, look at the equations that you have, and just do something with them. So, if you know the partial pressure of CO2, you know your temperature, and you know your Henry's law constant, well, solving for this isn't too bad. And I didn't write down all the numbers. You can just recalculate this stuff. So this is what you want. You want to know what's the concentration of our weak acid, because we're going to need that to calculate the pH. Okay, so there you go. There's the Henry's. Take your Henry's law constant times your partial pressure of your CO2. I'm going to let you fill in those numbers. So there's your partial pressure of your CO2. Use the Henry's law constant that I gave you before. And with 2 sig figs, I'm not too worried about sig figs here, but I should be 1.3 times 10 to the minus 5th molarity. Just confirm that. And the only thing that's going to be different in this first step, for the second part, for 590 parts per million, is to make that 500.00590. That's fine. So that's step 1. That's easy. Just plug in chug or whatever you call it. Step 2 is a little bit more involved. Ultimately, what we're after is what is the H plus concentration. That's what we use to measure how basic or acidic something is. And again, if you need to go back and review your essentials of acid-base chemistry, please do that. And pH, the equation for pH is the negative logarithm, log base 10, not log base E, natural logarithm of H plus. So that's just math. So if you know this number, the pH is just that. And you've probably done that before. How do we do it? Well, here's how you do the equilibrium math. If you've had Gen Chem, you did a ton of these problems. This is how we teach it at Shippensburg. It might be a slightly different method, but the chemistry here is a tool, so we're not going to dwell on this too much. So how do we approach doing these equilibrium problems? Okay, this is, so you take H2CO3. I'm not going to bother writing AQ all the time just to save time. And it is going to partially dissociate into H plus bicarbonate. And the way we solve these, it may look complicated at first, but there's an assumption we're going to make that makes it very simple. We have, how much do we have of these chemicals initially? So if you want to write that down, I means initial concentration. So initially, we have 1.3 times 10 to the minus 5 molar. Okay. Once it gets into the water, it dissociates, but initially, since it's a thought experiment, there isn't any of this. Well, some of this has to dissociate into H plus and HCO3, into protons or hydronium, whatever you like to call it, H plus and bicarbonate. So some of that has to form, and because this is a 1-to-1 ratio, every time this splits up, we get one of this and one of this, it's going to be the same amount. So this is going to have to go up by some amount. That's going to go up by the same amount. Oh, by the way, I'm sorry, C, that means change. And then this is going to go down by the same amount that those two go up. I'll let you think about that stoichiometrically, but don't overthink it. Then you simply combine those two, and now you have equilibrium. We call these ice tables, initial change equilibrium. So this is going to be, the equilibrium concentration is going to be 1.3 times 10 to the minus 5 minus x, and that's just x and x. Okay, where does that get us? That gets us where we have one unknown. X is our only unknown, and we take the ratio of this divided by this, and that's called Ka, and we solve for x. So let's see, I'm going to set this up right here. So our equilibrium constant, which is the value I gave you before, what is it, 4.5 times 10 to the minus 7, I guess I can write that. Again, if you want to put units, the units there will be molarity. Well, that's going to be H plus times HCO3, but that's x times x, so that's x squared, over 1.3 times 10 to the minus 5 minus x. Okay, if your algebra skills are pretty, what's the word I'm looking for, are pretty good, which hopefully they all are, you're scientists, is you could solve this equation using the quadratic equation. You would bring this over here, distribute that, set up your equation, ax squared plus bx plus c equals 0, and the quadratic equation is negative b plus or minus. Okay, you can do that. In fact, I encourage you to solve this using the quadratic equation, solve for x. But we can actually be smart about it. If you've had Gen Chem recently, you see exactly where I'm going. We're going to assume that x is really small, because this is a weak acid. This is a really weak acid. 10 to the negative 7 is a very small equilibrium constant. That means that not much of this dissociates. So we're going to assume that compared to 1.3 times 10 to the minus 5, this x in the denominator is approximately 0. Now that can be confusing, especially to Gen Chem students, but that doesn't mean that this x is 0, because that would be probably pointless. That this x compared to the initial isn't going to change it much. That simplifies the math. And again, if you need help with the algebra, I'll help you with the algebra. But so now we have a situation where we can simply solve for x. And I'm going to say approximately here, because we're making this assumption, is going to be the square root of 4.5 times 10 to the minus 7th times 1.3 times 10 to the minus 5th. More of a calculator exercise. And then I came up with 2.4 times 10 to the minus 6. So what does that mean? Well, that means x is 2.4 times 10 to the minus 6. And the units here are kind of important because that's a concentration. That's a molarity. And that also, from the chemistry, is equal to the H plus concentration. Well, put it into the equation. pH is negative logarithm of that number. I'll let you do that. So, therefore, the pH equals 5.6, which is slightly acidic. Well, that's slightly acidic. I mean, you can look up, I don't know if I have a graphic here. It's like, that's 7 is neutral, right? So 5.6 is less than that. Something like soda, you put a pH probe, it gets down to like 3. So it's much more acidic than this. We'd be in serious trouble if we had water that was that acidic. It happens, believe me, it happens. Okay, so that is natural acidity and the math. So be able to do those kinds of calculations, but again, it's not a Gen Chem class. So you use Henry's law, the interface between gas and aqueous. That's a very important law to get your carbonic acid concentration. Then you use equilibrium math to get your hydronium H+, and calculate a pH. That is standard environmental chemistry right there. I think that's where I'm going to stop this first video.